this video, we're going to look at some simple examples of equilibrium problems. In later videos, we'll look at some examples of some more involved problems involving equilibrium and equilibrium constants. So in these first couple examples, we're just asked to write the equilibrium constant expression for each reaction. And so writing down the equilibrium constant expression is fairly easy. It's just K. That's what we use to represent the equilibrium constant. Be sure to use capital K to distinguish it from the lowercase k that we use for rate constants. And K is just equal to the product of the concentrations of the products divided by the product of the concentrations of the reactants. And so my numerator is just the concentration of N2 times the concentration of H2, but I need to take into account the coefficients from the equation. So because there's a 3 in front of the H2 in the balanced chemical equation, I need to cube the concentration of H2. And for the reactants, I divide by them, so they go in the denominator. And because there's a 2, I need to square the NH3. All right, let's do another example on the next slide. Okay, so I have a new reaction. There aren't any coefficients, so I better make sure that it's balanced. I've got 3 hydrogens on the reactants, 3 hydrogens on the products, 1 fluorine, 1 oxygen, so we're good. So it's already balanced. So now we just have to write the equilibrium constant expression. So again, I'll have K is equal to the concentration of F minus times the concentration of H3O plus, and then divided by the concentrations of the reactants. So I have HF, and I won't include the water. So I only include gases and things that are aqueous in my equilibrium constant expressions. If I have solids or liquids, they have a value of 1, and so they don't appear in my equilibrium constant expression. So only things that are aqueous and gases. So I leave the water out. It just has a value of 1. And we'll do another example of this on the next slide. Okay, I have another chemical reaction. It's also balanced. This one has a solid, though, and so I'll leave the solid out of my expression for the equilibrium constant. So again, I'll have K. I only have one product, and it's a solid. It has a value of 1, so my numerator for the products is just 1. And then I'll divide by the concentration of P4 and the concentration of O2 to the 5th. All right, on the last 2 slides, we've got some examples of calculations involving K. Okay, in this example, we're given the reaction of ammonia to form nitrogen and hydrogen, and we're given the equilibrium concentrations of all the reactants and the products. This was the first example that we did, so we already wrote Kc, so I've just written it off here to the left. So all I need to do now is take my equilibrium concentrations, plug them into my expression for Kc, and I'm good. All right, so Kc is equal to concentration of N2 times concentration of H2 divided by the concentration of NH3. But I need to remember to take into account the exponents. So the hydrogen needs to be cubed and the ammonia needs to be squared. So the expression I get for Kc is, or the answer I get when I plug that into my calculator is 9.01. Now if you'll notice, I didn't write any units on Kc, and I didn't include any units when I was plugging the concentrations into the expression. That's because equilibrium constants, by definition, don't have units. And so I won't worry about including my units when I'm doing the calculations. And one thing I should have said at the beginning, you notice on the previous slides I used K, and here I'm using Kc. So when we do equilibrium calculations, I can either express my amounts of products and reactants in concentrations, as I've done here, or in pressures. So sometimes, to be more specific, if I'm using concentrations, I'll call it a Kc, or if I'm using pressures, I'll use a Kp, as we're going to do on the last example. In this problem, we're given the equilibrium constant, and we're given the equilibrium partial pressure of NaCl and Cl2, and we would like to know the equilibrium partial pressure of NO. So the first thing I need to do is write down my equilibrium constant expression. And so I write these as partial pressures as opposed to concentrations. All right, and all I need to do is plug in my value of the equilibrium constant, plug in the two partial pressures that I know, and then I'll be solving for the pressure of NO. Now, one note about units. We always need to be careful that the partial pressures that we plug into our equilibrium constant expression are always in atmospheres. If the problem gives them to us in torr or millimeters of mercury or kilopascals, I need to first convert them into atmospheres before plugging them into the equilibrium constant expression. And likewise, for KCs, I need to be sure that my concentration is in molarity, although I think that one is less likely to be an issue. So I plug in my value for Kp, and that's going to be equal to 28.2 squared over the concentration of NO is what we're solving for, so that's going to be x squared, and then the concentration of Cl2. All right, so I need to solve for x squared, so I need to get it out of the denominator, so I'll multiply both sides by x squared. All right, then I'll do the arithmetic on the right-hand side. Now divide both sides by 6.5 times 10 to the 4. And then finally, I'll take the square root of both sides to get x. All right, and as long as we're careful and always use atmospheres when we're working in with KPs, when we'll calculate the partial pressure, our result will always be in atmospheres.